Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics, please consider subscribing because you're in the right spot. That said, let's get in the current video. In this video, I'm going to take a look at the inverse of hyperbolic functions. In particular, I'm going to show you how to find the inverse for the hyperbolic sine. We can do a similar procedure for the hyperbolic cosine and the other trig inverse hyperbolic functions. First and foremost, recall that the hyperbolic sine is defined as e to the x minus e to the negative x over 2, where it's actually a linear combination of exponentials. Hyperbolic sine, again, here's its exponential definition. Also, recall, given a function of the form y equals f of x, to find f inverse, we take this, think of it as an equation, and I'm going to write this as x is equal to f of y. In other words, I just interchange the x and the y's, solve for y, then y is going to be equal to the inverse function. And notice that should make sense, because if I take if y is the f inverse, if I take f inverse and plug it in here, that means I'm taking the composition of those two. F composed with f inverse does reduce down to just x. If you are unfamiliar or a little unsure of what I just mentioned, please watch the video that I posted, I don't know, like a week or so ago on finding inverse functions. I kind of elaborate on that idea. That said, let's go ahead and find the inverse hyperbolic sine. So for example, find the inverse hyperbolic sine function. Okay, and I want to find it in a closed form so that if I wanted to evaluate this, I could know what expression to plug it in. Okay, so here's the solution. What I have for the hyperbolic sine is, let's say I've got y is equal to hyperbolic sine of x, which is equal to e to the x minus e to the negative x over 2. And as I reminded you, in order to, if I have a function of this form, in order to find the inverse, I set up this corresponding equation, which gives me, in this case, x is equal to e to the y minus e to the negative y over 2. And then I have to solve this equation for y. Now, first thing, let's go ahead and get rid of that denominator. So I'll multiply both sides by 2. That would give me 2x is equal to e to the y minus e to the negative y. To solve for y, again, I have to, you might think I could, well, add this over and then take the natural log, but then I'd have a y on this side, and I got to get the y's by themselves. You might say, okay, what if I take the natural log of this expression as is? Well, there's no property that if I have the natural log of a difference, I can then, say, cancel anything. So there's really no way that I can use a logarithm at this stage. So what I'm going to do is do something completely different. I'm going to multiply both sides of this equation by, that doesn't show up very well, let's do this one. Multiply both sides of this equation by e to the y. Okay, multiply both sides of the equation by that, and then we will put everything on the same side. E to the y times e to the y would be e to the y squared. E to the y times 2x would just be 2x e to the y, but then I'll subtract that over, giving me negative 2x e to the y. And notice that this term right here, yes, power to a power you multiply, so I could have written this as e to the 2y, but I'm leaving it this form for a reason. I'll explain in a moment. And then e to the y times e to the negative y, well, that would be, again, multiply. If the bases are the same, you add the exponents. Negative y plus y would be 0. E to the 0 is 1, so that means I would have minus 1. Now this was, remember, I subtracted this term over, so to write this as an equation, I would have this whole thing set equal to 0. Okay, In order to solve this, well, notice that I've got square of e to the y, I've got e to the y, and then I've got a constant. And the coefficients of those are either constants or at most expressions in x. Therefore, this equation is a quadratic equation in the variable e to the y. Okay. Well, quadratic equation, we've got a very simple way to solve those just using the quadratic formula. So let's go ahead and use the quadratic formula on that. So using the quadratic formula, okay. Again, my variable is e to the y. A lot of times, like in your beginning algebra courses, what you'll do is you'll make the change of variables. You'll say u is equal to e to the y, and then I'll rewrite this equation as 0 equals u squared minus, let's say, 2xu minus 1. We'll use the quadratic formula for the variable u. And then after we do that, we'll replace u with e to the y. But what I'm going to do is I'm just going to say e to the y is my variable, and rather than using that substitution. We'll get to the same place anyway in one step. Okay, so I've got e to the y is equal to, so then using the quadratic formula, remember it's negative b, where b is the coefficient of the first power term. That means I would have negative 2x, so negative b, plus or minus the square root of b squared, so that'd be negative 2x quantity squared, minus 4 times a. A is the coefficient of the squared variable, so that'd be 1. And then c, which is the constant term, so that's negative 1. And then all over 2a, where again, a is the coefficient of the squared term, so that gives me 2 times 1. All right, now this gives me e to the y is equal to negative is positive, 2x plus or minus the square root. Square of negative 2x would be 4x squared. Negative 4 times 1 times negative 1 would be plus 4. And then all over, more ink in there, all over 2. And then notice within the radical here, I could factor a 4 out. So I get e to the y is 2x plus or minus the square root of 4 times x squared plus 1 all over 2. Now I've got the square root of a product, so that's the product of the square roots. Notice that 4 is a factor and it's a perfect square. That means I can take a factor of 2 outside the radical. So I get 2x plus or minus 2 square root x squared plus 1 all over 2. What that then allows me to do is cancel a factor of 2. And let's see, I'd like to try to leave all this up here. So let me see if I can, what color would work here? I guess it should stand out. Okay. Then if I cancel a factor of 2, I'm going to get e to the y is equal to x plus or minus the square root of x squared plus 1. What I've been able to do so far is I couldn't isolate y just yet, and of course the next step should be clear what I'm going to do, but what I isolated the one term that has a y in it. And of course, to get rid of the e, I'm just going to take the natural log of both sides, which gives me y is equal to the natural log of x plus or minus the square root of x squared plus 1. And let's put that in, nope, let's put it in parentheses. Okay. Now, basic idea of a function is that one input would give me one output. But look at this expression right here. Is that the inverse? Well, notice I've got this plus or a minus here, which came out naturally through the quadratic formula. If I was to plug in a constant, I could get x plus a number and then x minus a number, so I get two different outputs. So the idea that we have to figure out here is plus or minus. And I'm going to show you a very straightforward way to do that. So let me go ahead, pause the video, and then I'm going to clean this up, and then let's kind of elaborate on how to determine if it's plus or minus. Okay, so again, we have to determine is it plus or minus, so that way this expression here does actually represent a function. Well, before I show you how to do that, let me first of all recall, if I have a function value, say f of a is equal to b, then in this function that say has an inverse, then that tells me that f inverse of b is equal to a. Remember, the inputs and the outputs switch. For a really quick example to illustrate that, if the function f of x is, let's say, x plus 3, then of course the input or the inverse is x minus 3. And if I look at the function value f of 4, of course that's equal to 7. And then if I take f inverse of 7, that'd be 7 minus 3, which is 4. It's 4. So again, for in a function that's inverse, the inputs and the outputs switch. Well, that must be true in this case as well. So the question is, which one will actually work out, the plus or the minus? Here's how I'm going to check this. Let's say f of x is equal to, so again, the hyperbolic sign of x, which once again we know has an exponential definition. And what I'm going to do is I'm going to plug in a convenient value. I'm going to plug in, you could say, well, if I plug in 0, that's a pretty nice number to just do some computations with. E to the 0 is 1, e to the negative 0 is 1, so I get 1 minus 1, which is 0. That says that f of 0 would be 0 in this case, but then the inverse would have to have f inverse of 0 is equal to 0 as well. And I guess you could do it that way, so I guess that would be a simpler example than what I was going to do. So let me go ahead and go through this one first, and then I'm going to go through a slightly more complicated number just for illustration purposes. The idea is that if I plug 0 in for x for the inverse function, the output should be 0. Let's go ahead and plug that in. I know that I should have 0 is equal to the natural log of 0 plus or minus the square root of 0 squared plus 1. Okay, well, 0 squared plus 1, of course, is 1. Square root of 1 is 1. That would give me 0 is equal to the natural log of, and then 0 plus or minus anything is just plus or minus anything, so that would give me plus or minus 1. Problem is the natural log, well, not really the problem, but the reasoning then is that the natural log has a domain of 0 to infinity, and of course the only value that's in that domain between these two numbers would be positive 1. Therefore we had to have the positive from the beginning, and that means that I'm going to use the positive in the expression for the inverse hyperbolic function. So therefore the inverse hyperbolic sign is given by the natural log of x plus the square root of x squared plus 1. Okay. Now it should seem, I mean, if I go from this expression right here, and this is the hyperbolic function, this is the inverse of it, it's not completely clear, obvious how I went from this to this, but there should be a few things there that seem at least reasonable. The hyperbolic function is based on the natural exponential function, and the inverse hyperbolic sign is based on the natural logarithm, which of course that's the inverse of the natural exponential. So that should at least seem intuitive somewhat. And then of course I've got a subtraction here, and here there's an addition, and the others like the square and the square root that might not be completely analogous, might not see where that comes from. But the idea is that this is then the expression for the inverse hyperbolic sign. Thank you for watching, and please consider subscribing.